Hello, friend. Today in this video, we're going to be continuing looking at applying deep learning for like text processing tasks. But up to this point, we've learned a lot about recurrent layers and neural attention and things that can be useful for processing text and sequences in general. But we've most of our examples, I think all of our examples, we've looked at image classification problems. So in this one, we'll look at another common sort of text processing, sequence-to-sequence learning. So this can be applied to lots of things, but we'll be using an example, a simple machine translation example in this video. Okay, so if you're ready, let's go ahead and get started. Okay, so up to this point, you've seen probably all the tools that the main ones that you would need in order to do text processing and sequence processing with deep networks. But our examples up to this point have been basically from doing classification problems. So the IMDB database is a kind of sentiment analysis, but it's really a binary classification, so positive or negative reviews. So there's a lot more to natural language processing than just classification. So another common area that's used a lot are the so-called sequence-to-sequence models. So a sequence-to-sequence model takes a sequence's input and translates it into a different sequence, all right? So there's a lot of use cases for these. So we will be using a machine translation, simple one to try and translate an English sentence into a Spanish sentence. But yeah, I mean, machine translation, the state of the art that you would find out there on Google or other places are using this kind of deep networks with sequence-to-sequence models. And there's lots of other use cases like text summarization, convert a long document into a summarization of it, question answering, chatbot. So in that, you can take a prompt and try and convert that to a sequence of like a conversation, and text generation. So large language models, fall into this. They're instances of this kind of text generation using these same sorts of sequence-to-sequence models. So the general template that's used to build one of these kinds of sequence-to-sequence models that will translate from one sequence into another sequence is shown here in this diagram, okay? So basically there's two parts to a sequence-to-sequence model. An encoder model. So the purpose of the encoder model is to transform the source sequence into an intermediate representation. So again, if we're doing English to Spanish translation, the encoder will get an English sentence and will transform this whole sequence into a compressed intermediate representation here. I'll just say rep here, okay? And then the other part is a decoder, okay? So the decoder is trained. So there is some trainable parameters over here in the encoder, for example, like your embedding layer, maybe some other stuff. But the decoder is easier to understand how it's trained. So it's going to be given a sentence. It's actually going to be given a sentence of some previous tokens. So the tokens from 0, which will always be a special start token, up to some current token. So let's say we've only said the first 2 words so far. And it will also be given the intermediate representation of the source language as input. So the decoder in the model here gets 2 inputs: the intermediate representation from the source and the sequence, the destination sequence up to time step in. So the model's task is to predict the next token. So what should occur at n-1? So if we were at tempo here and we wanted to predict haste, the label that we would be training with would be this word here, the n-1th word in the input. Okay. So and what I was just describing there was the what happens during training. Okay, so that's how we build the model, and that's how the weight in the decoder and some of the weights here in the encoder will get modified in order to, reduce loss in this task to try to predict the next words. I should have said the nth word, given the words in the sequence from 0 to n-1 here. Okay? And then during inference, we don't have the target. We don't have the input target. So what we do with inference is we use the same encoder and decoder train, and the weights are going to be frozen. So we're not doing any learning in inference. So this is for production when we want to actually translate an English sentence into Spanish. So the way it works is, we have the same encoder, which will translate our intermediate representation again. And so that'll be one input to the decoder, and we will give it just the special start token to begin with. And we'll ask it to predict the next token after that. Okay. So once it's predicted token 1, then we just keep repeating that, right? So once it's predicted token 1, we give it that and the first token it predicted, and we ask it to predict token 2. All right. And then when we have the start 1 and 2 token, we ask it to get the third token. And we keep doing that until either some maximum length, whatever we decide was the maximum length for our outputs, or until it gives us the special end token, at which point we'll stop. All right. So that's the basic idea. And you can use recurrent layers for both the encoding and the decoder. So we'll look at that, and we'll also look at, in this video, using the transformer architecture to be the encoder and the decoder piece in this video. Okay, so for our machine translation example, of course, we need a appropriate corpus. In this case, we need a corpus that has, sentences in English, and then their corresponding Spanish translation. So sequences in the source, and the sequences in the destination that we want to translate to. So we use this corpus here. So again, it's a little bit too big, so I've already downloaded this. And if you're using this notebook from this video here, I expect it to end up in a directory in our data subdirectory for the project called SPA-ENG, Spanish to English. And it's really just one big text file. So if you take a look at this text file, you'll see that it's really kind of small phrases, sentence level. Some of them are even shorter than that. English, and then there's a tab separator. So the separator that's used between the two sequences. So there's one pair of sequences per line. There's a tab separator, and we've got the English before the tab and the Spanish after the tab. Okay. So, so it's relatively easy to parse. We don't need anything. Well, we will have to use vectorization and our embeddings and stuff as usual. But our first step is we're going to have to read the file and split them by that tab, so we get our pairs here. So that's all this first little bit of code is doing, is creating just a regular Python list of the pairs here. So we have pairs of tuples in the English and Spanish. So for example, again, we can pick a couple of 5 choices at random here. Yeah, I forgot to mention, so we're using a special token here, so we're going to end up having this embedded in our Spanish vocabulary here, so the start and end token. So we need that for the decoder part. So every Spanish sentence should have a special token that comes in, so it starts off just as, text with brackets here, but we're gonna have to not remove the square brackets when we do our normalization of our Spanish text here. But that will be part of the thing that's learned by the encoder, that everything starts with this one token and ends with the other here. Okay. So yeah, if you look at that, there's a bit over 100,000 pairs that we have here. So not too big, but relatively big. And kind of as a warning, these encoder decoders are a bit computationally expensive, so it is going to be tough for some people to run this notebook, especially if you don't have a GPU. So we will randomize it up front and do a validation split by hand. So after randomizing it, we'll hold back 15% so that we can use for validation during our training of our data sets. So in previous talks, we've given some examples of the step here so you can see it in action for this data set. So, we do need to do a text vectorization to normalize the sentences and tokenize them. So I already mentioned that we have a little bit of some special stuff that we're going to use for the Spanish vocabulary. So we are still stripping punctuation like we've done before. There's a lot of the Spanish end of question, so we'll add that in, get that out, but we are going to not strip out any square brackets, so probably we could go and find this out, but probably there's none of these anyway, so we can have those safely as our special start in tokens here. So so we use this is, remember, is the object that will do the normalization and the tokenization that we need, so we can feed this in to build up an embedding. So we are keeping sentences or sequences to 20 at most, so relatively short phrases or short sentences here. It's basically the same thing, except one of these is going to be using the English and the other one will use the Spanish. And so for the Spanish one, we have to have it use our custom standardization function. So here, remember, this is our step where we're actually building up the vocabulary index or the vocabulary dictionary for our two different texts that we have here. Okay. So we're ready to, we need one of the TensorFlow data sets so we can use it to stream in things we need. So basically here, notice what we're doing is when we get English and Spanish sentence, we use our setup vectorizers to normalize and tokenize it. And from those, we're going to actually be returning a dictionary. So that has two keys for the English set of things that's returned from the vectorization in the Spanish. And again, basically the encoder is predicting the nth-1 word. So we strip off the last one, and then the labels are going to be what's used for the targets for the decoder part of our translator here, right? So it starts at the next token. So it starts at token 1 and goes to the last token, right? So so here we're using a batch size of 64. This actually creates the TensorFlow data set. So, you've kind of seen this before. We actually put it through a couple of steps here to create it using our, strings. We set the batch size, and then we use that special function up here so that it will actually be formatting the returns into this dictionary. And so just to be clear, again, we can iterate over one of these things. So if we take out the first item, you'll see that the inputs is a dictionary, and the shape, since we set the maximum size for our sentences to 20 is, in our batch size is 64, these come out as 64 by 20 shaped. So these are still the integer sequences, and they're padded by zeros, and you also should notice that the target is offset by 1. So the target is also the Spanish sentence is also the same shape, but offset by 1 here with the target. So the simplest thing you could do to do this sort of prediction of the next token in the target, the destination sequence, is just keep the output of the RNN at each time step, right? So remember that is this parameter here, right? So returning sequences. So we would be getting the whole outputs from doing the iteration over the sequence from 0, 1, 2 up to the 20th token in the sequence done to the dense layer. And you could use that as a way of predicting what but the main problem is that if you're doing that, I mean, both the source and the target sentences, so both the English and Spanish, are being processed sequentially from 0 to n. So that means that if I'm trying to predict the next token, n+1, I'm only considering in the source language, those same number of tokens of input. So like it says, it's like trying to predict ill from just seeing the first word in there, right? And so on. So I mean, that's not the way that a usual human translator would go about doing the prediction. They would read the whole sentence and then craft something in the target language that would be the kind of the best translation, and it doesn't necessarily going to have the same word order and things like that. So the proper sequence to sequence setup is we need the encoder that's going to turn the entire source sequence into a single kind of compressed representation. So we can give the whole history or just the final vector as output from that. And that would be fed into the decoder. So the representation of the whole source sequence as well as the target sequence up to 0 to n to predict the n+1 item in the target sequence. Okay, so let's go ahead and try and implement that in the architecture we looked at before, the encoder-decoder architecture. So let's take a quick look at the encoder here. So this is expecting just the the vectorized representation of the English sentence coming in as input. We are doing a word embedding, so it is going to be learning a word embedding for the English vocabulary that comes in here. So that's one of the things to learn. And as usual for the encoder, there will be some learning happening in GRU, so that will get modified by gradient descent on the loss function. I did give a name here, so when we look at the summary, we can see this. But we're using 1024. Again, you can think of that as the kind of the power of the output representation that comes from the recurrent layer. If you remember, for a bidirectional layer, the default is just to concatenate the two bidirectionals together. So you get 2048 in that case. So the book doesn't discuss this, but they did show using a sum here, so you actually get 1024 out of your encoder if you look at the summary, which is the sum of those things. So I'm not certain what the advantage would be of that. I would think that concatenating might give you a little bit more information, so that might be a parameter you could try to change to see if you get better performance on this. So that's the encoder. So this is the thing that handles the English sentence, and we're going to use the full output from that's coming from here, the encoded source, to input into the decoder. Okay, so the decoder happens in this layer here. So we're going to input in the input for the Spanish sentence coming into here, and it's going to learn its own embedding of the Spanish vocabulary. And we're using the same GRU layer. So I don't know if there's any real reason to choose GRU over LSTM. So they're usually pretty similar in performance. But we do the same thing on the decoder for the GRU recurrent layer that we use. So the same number of latent dimensions, although notice that we are returning the sequences. So it's another thing I should have mentioned here. So by not returning the sequences, we only get the final output that we feed into the decoder here instead of the sequence. But this one will return the sequences because we are doing that predict the next token from the current token task here, kind of like we were talking about in the naive approach. But yeah, so here's the tricky part, right? I mean, kind of tricky. So here is how we end up passing in the input from the encoder into the decoder state. So the initial state is going to start with the full encoded source. So yeah, I mean, the way this works is this is going to give one representation, since we don't save the history, of the full sequence that's run through here. That becomes the initial state for our decoder recurrent layer here, as well as the input coming in from the embedding. And a note on this, I'm having a problem with the example. I haven't been able to track it down because this example will take some time to run, so I'm not really, I don't see the same performance that the textbook notes here, so I'm not certain what the issue is. So if anybody kind of knows, I haven't been able to find a discussion of this. It does look to me like it is not really, it's still underfitting. So I did remove the dropout layer, but they showed some dropout on here. But this is kind of the summary. Actually, let's display the model architecture as well. Yeah, so I already did that here, so you can do a little bit better. So you can see over here is the encoder, where it goes to the embedding, and this is the GRU part of the encoder here. So it ends up outputting just one with the 1024 output, because it sums together the forward and backward one. So that comes into the decoder as the initial state, as well as it gets the embeddings for the Spanish coming in over here. So yeah, it's actually getting two inputs, the embeddings in 256 dimensions and the initial state from the encoder here. And it outputs the representation is going to be, it's going to have the 1024, but it's also going to have the full history that goes to the final dense layer that we use to interpret what the prediction for the next token is in this case. All right, so as I mentioned, there's still kind of an issue with this example, and also this will take some time, so you may not have the computational budget to run this full example here. I'll go ahead and run it, and I'll kind of discuss it both the way that the textbook thinks this should be ending up a result, and what we actually see here. Right? So, like I said, I modified just a little bit. I did remove the regularization for the dropout layer, what we're doing here. Otherwise, it's pretty much the same as the second edition textbook version of this. So let's go ahead and let that run and see what we get. Okay, so once that's finally finished, so like I said, I kind of removed the regularization, so we removed the dropout, but my observation is we're not getting kind of the validation accuracy, so I'm not too certain why. And if you look at the loss, it's maybe still going down, but the validation loss seems to stall, but it doesn't seem to be overfitting. So, for example, let's see, let's plot the dictionary here, the learning curves here, just to see what it looks like. So yes, what I'm getting after 20 epochs without any dropout. So, so yeah, I mean, maybe it's kind of on the edge of overfitting, but yeah, I would like to drive that down more and see if we can get the validation loss to go down. So, anyway, so with what we get, so if we want to try this out, we basically have to use the trained model and feed it in a sentence. We have to kind of by hand do that loop where we start with the start token and ask it to predict the next one, and then basically keep doing that until we hit our maximum sequence length with the 20, or until we hit the end here. So that's what this decoding is doing. So for the textbook, as a reminder, it's expecting more like a 67% accuracy. It's not clear, but I think 67% accuracy on the test accuracy. So I don't know what that translates to on validation accuracy. Accuracy isn't a real good metric here. So the textbook discusses this a little bit. You would most likely want to use something else. So there's a specific one, this BLEU, for doing translation, right? So, but this gives you a little bit of at least some idea of maybe what it's doing, at least, how often it's predicting next token. And remember, this is, so like a baseline of random would be almost 0%, right? Because the vocabulary, we had 15,000 words. If you're just picking a random word next, you get almost 0% accuracy. So it is doing something, although, yeah, again, I think it's still kind of underfitting. at least what I'm seeing here. So, and that comes out to that the translations don't particularly look all that great for this one, or even for the transformer model. But, you know, it does a little bit. So I modified this so that we get the English sentence, we get the decoded output sentence by, you know, using the inference process inside of this decode sequence function here. And for reference, since I'm not really fluent in Spanish, I get kind of what the actual target sentence was for the input sentences that we randomly selected here. So, okay. So anyway, there's many things we could do. I kind of think it's under, so it's not overfitting, so we're still kind of underfitting. So probably I would try some of these. Use a stack of recurrent layers, maybe change that from summing together to maybe concatenating to return both the bidirectional, you know, the forward and the backward direction from the encoder layer. So, so to summarize what we just looked at, using a straightforward RNN unit to try and do an encoder decoder sequence to sequence learning. So, you know, the source sequence representation has to be held entirely in that encoder state that gets sent to the decoder. So that puts a severe limit on the size and complexity of the sentence that you can translate, right? So, in general, recurrent neural networks, even LSTM or GRU, are going to have trouble dealing with very long sequences. So they tend to progressively forget stuff. So both of those are kind of the reason why transformer encoder decoders have been embraced. They add in neural attention, which kind of helps with these tasks. So able to handle much larger sequences. Okay, I'm going to break this video in two though, so we'll go look at the transformer encoder decoder and see how you implement that. All right. So so just a couple of other summary things for this part of the video. So the sequence model takes a sequence as input and translates it into a different sequence. All right, and so you saw the basic architecture of that. We'll have an encoder and a decoder. Is how we usually do a sequence-to-sequence model. And the point of the encoder is, you know, if you want to predict the next token in order to generate a new sequence from the tokens you've seen so far, you can't really, you know, for your source sequence, you can't restrict yourself to only the first n tokens. That doesn't work. It's not how a human would do translation. So the encoder model turns the source sequence into an intermediate representation. So it turns the whole source sequence into this intermediate representation, which gets fed into the decoder. So the decoder is taking that intermediate representation and the first n tokens of the target sequence, and it learns to try and predict the next token in the target sequence. So that's the basic way that the encoder decoder works. All right, so that's it. Stay tuned then to see the next part where we will try and do this with a transformer architecture, transformer encoder.